We'll talk about electricity generation today. So we've already talked about the grid, talked about battery storage, making it more reliable. We've talked about ancillary services a little bit. We talked about different markets on the grid. Today, we're really going to be talking about the generation side. How do we make the electricity that's going on the grid? And mostly we're going to talk about thermal power plants. Still the biggest piece of our electricity generation. We'll talk about solar when we get to the solar lecture. That's the other big piece. And wind and other things. Today, we're really going to be talking about thermal. Hopefully you know this reference. This is from Back to the Future. A lot of times you keep saying 1.21 gigawatts. We tend to say gigawatts in the industry. Gigawatts is not the normal way we talk about electricity. So just like to bring that. I want you guys to know the lingo. It's usually a hard G when we say gigawatts, unlike Professor Brown. Okay, and then this is the book I'm passing around. What I'm dressed up as Miss Frizzle. So electricity, secondary energy, right? It's not a primary resource. We have to make it from something else. It's an energy carrier. Fossil fuels still dominate for our electricity production. So you guys have seen that already. We're still very much using fossil fuels. That's why we're going to really talk about thermal power plants today. A lot of options, though, for electricity generation. So unlike when we see transportation, we really only have oil as really a dominant liquid fuel. It's really hard to make other liquid fuels that compete with it. In the electricity sector, we have lots of options on how to create electricity. And once you have that electricity, it's the same, right? It's that electricity resource is just electricity, no matter where it comes from. We're going to talk about some of the environmental impacts, especially from our thermal power plants, right? It's our air pollution and greenhouse gas emissions that we worry about. And then there's other environmental impacts, which we talked about some like in the coal lecture, right? We have coal ash, things that are left over. And then, of course, we have land use impacts too from things like our transmission and distribution. So there's a lot of other environmental impacts we talk about. We've seen the charts about efficiency, and we're going to talk about what a heat engine is today, so you can really kind of solidify in your mind why it's so inefficient to use these thermal resources to produce electricity. But our average conversion efficiency for the electricity system is 35%. That's like the average overall in terms of the electricity we're producing. It matters, especially for things that have other impacts, right? You can think about efficiency matters, thinking about what the impact is. So what I mean by that is like a solar panel, some of our best solar panels. Does anybody know how efficient our best solar panels are? Like 20%. Okay, so it's not super efficient, but you have to think also about what does that efficiency mean? For a solar panel, it means you need more area, right? Because if you have more area, you're just converting sunlight into electricity. So that efficiency translates into land use. Right? If we can make it more efficient, we need less land use for that solar production. For something like a coal-fired power plant, that lower efficiency means more coal burned for electricity production, and that's air pollution, climate change, coal ash. So efficiency matters, but also you have to think about what are all the other impacts on that resource that you're deciding to use. Okay, so we're going to talk more about that. And just to remember, we've already kind of talked about, electricity must be balanced, supply and demand in real time. Otherwise, the frequency goes off the chart, right? Like Simon in the video. And everything will shut down. The thermal power plants will shut down to protect themselves because their electricity generators only operate at a certain frequency range. So the grid will actually shut down if we're not operating it right near that frequency. Electricity is hard to store, obviously, as electricity. Capacitors, kind of the only way. But we can store it chemically in batteries. We can store it in potential energy and pumped hydro, which we talked about on Wednesday. That helps the resiliency and the reliability of our grid to have storage, because then we have some leeway about supply and demand, right? We can meet both variability in supply, which is our renewables oftentimes, and variability in demand, which is just how we utilize that electricity. It needs backup, so we talked about capacity reserves as one of the markets, and of course, Kirsten talked about it's not just about how much it costs, it's the value. So you've already seen this. Today we're really going to be talking about electricity generation. So before we get into how it's made and what happens, let's just do some significance of our electricity system. So you guys have seen charts like this before. We just talked about it's very fossil fuel dominated. You saw in your Kahoot, right? Coal is what dominates in the world. In the United States, it's natural gas. This has been a growing phenomena, right? 2007 was the peak of coal. It's been dropping since 2007, taken over by natural gas, wind, and solar. With solar the fastest growing, but it was from a very small percentage when it started. It varies by region too in terms of electricity generation. So here I'm just showing you regions in the world and what type of electricity generation they depend on. And so it really depends on the resources. So Asia Pacific, we know China is very coal dominated. Places like Central and South America, very hydro dominated. That's a resource that is still very much growing in Central and South America and something they rely on a lot. You can see the Middle East, it's very much natural gas and even a significant portion that's oil in their electricity grid, something we don't see in a lot of other electricity grids. So here we are in North America, very much with natural gas and then the solar and wind. In Europe, a lot of solar, wind, nuclear, kind of like North America. So it varies a lot. You can also kind of get, we talked about this in the first lecture, that there's a lot of variation in terms of electricity demand by regions. Some of it due to population and demand in terms of how much manufacturing or things like that go on. So that's thinking about North America versus something like Asia Pacific. And then it's also just access and how big the electricity system actually is. And so you see places like Africa that still have a very limited resource, limited access to electricity generation. So some of these places are seeing growth, but a long way to go to be anywhere near some of the other regions. I just wanted to do a side note on China for a minute, because we talk about China a lot when we talk about each resource. Because it is coal dominated, this just gives you a sense it's seen growth in electricity demand as its economy has grown, growth in coal. But I also wanted to give you a sense that it is also still, it's the number one producer of solar electricity and the number one producer of wind electricity. So China has really tried to grow all of its resources, including coal, in order to meet that growing demand. And so we'll talk more about that as we get to it. But just think in a lot of these resources, it's number one. It's not just the coal-fired. And then I just like this to give you a little history of electricity, because electricity is a high-quality energy carrier. We can do a lot with it. Once we make electricity, we can run motors, we can run lights. It's a very versatile, what we call high-quality energy carrier. But we haven't been using electricity all that long, really, in human timescales. So we really started doing it really in the early 1900s is really when we started using electricity, when we started to see it in homes. It was early 1900s. Early on, for appliances, our refrigeration kind of really took off, things like that. And you can kind of see we started to really generate significant amounts of electricity not until like the 40s and 50s is really started to see a lot of growth, both in residential and commercial. So I'll let you read through this on your own if you want just some fun facts about electricity. One fun fact is, does anybody know when we started to sell the first refrigerator for homes? It was 1913, the very first refrigerator for a home. But again, that was really the start of seeing a lot of demand. And of course, today we see lots of demand for electricity in our homes. But that was the very first one that went on sale. They got more popular right around 1925. Fun facts. Okay. And then you've seen that this chart or something similar to this chart before, but this is just the electricity system. So those are our electricity resources. And the losses, and then kind of where they go in terms of end use. So much of it is into our buildings and industry. Some of this industrial includes buildings that are industrial buildings, and then very little right now into things like transportation. All right, so I'm evoking one character of science today as Miss Frizzle. Of course, we have to bring in another character of science, Bill Nye, to talk about how do we produce electricity.
So where does electricity come from, anyway? Well, in 1831, two scientists figured out how to make electricity. It was Michael Faraday, working in Britain, and Joseph Henry, working in the United States. At about the same time, they both did an experiment, something like this. Michael Faraday took a coil of wire and he moved it over a magnet. And when he did, electricity started to flow in this coil. The electricity went down over here to another coil and made a compass needle move. Michael Faraday was doing this experiment for an audience, and a woman came up to him afterwards and said, Mr. Faraday, of what use is it? And he said, Madam, will you tell me the use of a newborn child? And what he meant was, would you take a look? I mean, I'm moving the compass needle without touching it. You understand? I have a coil of wire way over here, and I'm making a compass needle move way over there with no apparent force. I mean, some force is going right through the air and wiggling that needle. Something's happening here. Some spectacular effect is happening here. You may not completely understand it right now with no apparent force. One day we will, and it's going to be a big deal. Thank you for joining me on Consider the Following.
All right, that is how we produce electricity for most of our electricity production is by moving a coil in a magnetic field or the other way around. You can do it either way. But you're basically, with alternating current, you're moving it through the magnetic field, rotating it through the system, or you can either move basically the wire or the magnetic fields in order to make that happen. So that is how, when we talked about, you've seen this slide from Kirsten, we talked about those rotating generators. That's how you're producing electricity. So all of our thermal power plants, a lot of our kinetic power plants, all of that is to create rotational mechanical energy in order to move those wires in that magnetic field to create alternating current. That is what we're ultimately trying to do there. Okay, so you guys want to see what this looks like for real? So what I've got, I'll pass this around. This is a little electric motor. Electric motor, electric generator, it's the same thing. It's just whether you're using mechanical energy to spin it, that'll create electricity, or you can put electricity into it, that'll spin it to create motion. So this is what you're using in your electric vehicle. It's an electric motor. They have obviously more sophisticated ones than this little electric motor. But you can see in this case, there's a magnet is on the shaft. The magnet is spinning, and you can see the coil of wires that are around it. You can do it either way. In this situation, you have the magnet around, and then you're spinning the coil of wires. Either way, you'd want that coil of wires, and that's what makes it oscillating. It's oscillating through that magnetic field. Okay? They do actually have DC motors too. You can look up, they get really sophisticated on how you can make different motors, but it's a very efficient way of converting energy from a mechanical rotational energy into electricity. So our electric motors tend to be highly efficient. It's part of what electric vehicles are so efficient. Okay, so this is just to give you a sense of scale. This is a very small electric motor. Electric generator, it's only like 90 megawatts. A lot of our power plants, they're going to be hundreds of megawatts at least. So much bigger than that generator. All right, so in order to spin that, we often use a heat engine. So with a heat engine, we're converting heat into work. That's a very lossy way to do things, but it is a very available way of doing things. So how does a heat engine work? You can imagine that heat as an energy type will flow from hot to cold. And so with a heat engine, you have a hot source and a cold sink. In our thermal power plants, that hot source might be something like burning coal. There's your hot source. You're heating up water to make steam. You still need a cold sink to draw that heat through. And so that's usually our condenser, our river water, our evaporator, something that is a cold sink. You need both of those for that heat to flow through. And as the heat is flowing from our hot source to our cold sink, we're able to extract work from it. We obviously can't extract all of the work, and so we lose a lot of that heat going into our cold sink. This is why it's not super efficient way of doing things. We have a very easy equation to figure out our conversion efficiency in a heat engine. So Carnot came up with this. There's a little picture of him, Carnot. The efficiency of a heat engine and the ideal world, like the best you could do with heat to make work, is 1 minus the temperature of that cold sink divided by the temperature of that hot source. Those numbers, and you're going to have to practice this, so those numbers have to be in Rankine or Kelvin. They have to be, you can't do it in Celsius or Fahrenheit. So you do have to convert your numbers before you use that efficiency equation. But this efficiency equation gives us a sense of how can we make a power plant more efficient. You can either make your tea colder or your tea hotter. Both of those things would make your power plant more efficient, right? In theory, right? Just as the maximum efficiency, ideal world efficiency you can get. Of course, we don't live in the ideal world. There's all sorts of other losses. So I wanted to give you a sense of this is the efficiency limit, ideal world, not including things like friction and all the stuff that we have to deal with in the real world. And this is what today's actual efficiency is. It's important to think about this because when we start talking about, oh my God, our steam cycle power plants, are only 30 to 40% efficient, we're not comparing that to 100, right? They can only be, maybe 60% efficient in the ideal world, right? We can't get all the way there. So when we were talking about solar PV being only like 20% efficient in the field, theoretically the limit's only about 34%, right? So we're not comparing it again to 100%. And so there are ways, this is talking about, we'll talk about solar, but single junction, that's what most of our silicon-based solar panels are. Multi-junction is like layered, it's much more expensive. We've talked about using it in space applications, things like that, where space is really important. So yeah, you can get more efficient, but what we're really putting out in the field is our single junction solar panels. So let's talk about the 3 main types of thermal power plants. And we've talked a little bit already about some of this. Base load, I'll just put up here, peaking and intermediate. So our base load power plants, these are our steam cycle power plants. We're going to go into more detail about this. But really, you have your hot source, your boiling water, you're turning a steam turbine. That's giving you the mechanical rotational energy to turn your generator and produce electricity. We consider those base load because steam is hot and it's running through metal pipes and metal equipment, and you have to heat that metal equipment up slowly because it will expand. And so when you're bringing a steam cycle power plant online, you have to do so slowly, and you don't want to vary it very much because the metal will expand and contract based on the temperature. And so that's our nuclear power plants, our coal-fired power plants. We bring them online slowly and we take them offline slowly. Because if you have sudden expansion or fast expansion of some of those things, you're going to start breaking pipes and equipment, separating the piping from the equipment. So it has to be done slowly. Peaking plants, our gas turbines, we'll talk about more of that in a minute. Think about that as like an airplane engine, and some of the original ones were airplane engines. So gasified fuel, we often use natural gas, but you can also gasify other liquid fuels to use in a gas turbine. Really fast. You can bring them online really quickly and turn them off. They're not very efficient. So you only want to use them when you have to in order to meet demand. You have to meet fast demand. And then combined cycle, this is where we've seen a lot of the growth in natural gases, combining those two. And we'll talk about how that's really advantageous to combine the two, both gas turbines and the steam cycle. All right, so let's talk a little bit more about our steam cycle for a few minutes. So like I said, in a Rankine steam cycle power plant, all we're trying to do is boil water. So we can use all sorts of different things to boil water. We can burn coal, we can burn natural gas, we can use nuclear, we can burn biomass, we can use geothermal, we can even use solar thermal. All of it is just to boil water. That is the goal of that resource and that heat source for a steam cycle power plant. Once we have that, we're boiling the water with whatever we're using, whether it's a fuel or something else. We have high temperature, high pressure steam going to our turbine. That's where we're extracting work. So that turbine is going to turn our generator and make electricity. We have to have a cold sink. Remember, this is a heat engine. So we have our hot source. We have to have some sort of condenser or something that is like drawing the heat through the system. And so that can be a cooling tower, it can be river or ocean water, whatever, something that's cold. And now you have low temperature, low pressure liquid, and you pump it back through. Okay, so that steam water is just reused over and over again through your power plant. You're putting in fuel and you're putting heat into your condenser. That's where a lot of your losses are. So just for a pretty picture on what that looks like. So if you have your coal coming in and you're burning stuff that makes steam, it's turning the turbine, condensing it back to water, making electricity for your city here. Let's do a quick calculation. You guys are going to calculate the efficiency, I'll give you a couple minutes, of this steam cycle power plant. So there's your efficiency equation. You have the temperature from the boiler is 1,000 degrees Fahrenheit and the cooling water is 75 degrees. What's your efficiency? So you had to convert it, right? You convert it, I did it to Rankine, but you can convert it to Rankine or Kelvin. Put it in your equation. Remember, we talked about 2 ways you can make your ideal efficiency more efficient, right? Colder cooling, hotter boiler temperature, right? Hotter source. Good. So a lot of those losses are going out through the condenser. Some of them are going out through the boiler. Want to take you through a few other ways that we can make these that are contributing to more efficiency in some of these power plants. So obviously, if we make our steam boiler hotter, that hot source is hotter, that's good. But one of the challenges is the materials that you need to be able to survive those level of temperatures, those heat. So we do have ways of also increasing the pressure. So you can see that like we can use supercritical, or we call them ultra supercritical, these other things that make it really high hot. But because it requires special materials, it's not always cost effective. We have seen in some of when China's seen a lot of growth in its thermal power plants. A lot of our thermal power plants here are old, but a lot of them are at least supercritical or ultra supercritical in order to get some of those efficiency gains. Okay, so then that steam comes into a turbine, and I just want to show you what a turbine looks like here. A lot of times it's not one. It can be 2, 3 turbines. What you have is like a high pressure turbine, medium pressure turbine, and then a low pressure turbine. And sometimes that third one is even operating under vacuum. So you're trying to draw as much of that energy out of the steam as it goes through these different stages before you send it to the condenser. So this is just showing you this one has 2 turbines in this. When we go to Lodi, which is one of the natural gas plants, they actually have 3 to just improve the efficiency in order to draw more of that energy out of the heat before you send it to the condenser. This gives you a sense. So this is a turbine, just to give you a sense of scale, so you can see the guy looking at it. These are like little blades. They're called buckets. I think because that harkens back to just thinking about like buckets and like a water wheel. They don't look like buckets, they're little blades, but that's what they're called on a steam turbine. If you ever get to go to the geysers, which is up in Northern California, we'll talk about it in geothermal. They actually have one of these out. You can actually go see a turbine out on a display at their museum, their visitor center. Okay, so we've pulled out as much of that energy out of that heat as we can from our steam. We send it to the condenser. This is just typically a typical version of a condenser. So what you're trying to do is cross-exchange that cooling water with your steam as much as possible. You want as much contact to provide as much cooling. And so what this condenser looks like, these holes are tubes where the condensing water is going through, and the steam is usually cross-exchanging with those tubes, and it's falling through the tubes. So you're trying to just have as much surface area between the water and the steam that's going through to condense the steam. So I used to work at Dow Chemical. I worked there for about 4 years before I came back to Stanford for school. We had quite a few of these condensers. We had a cooling system. We used river water as the makeup water for our evaporative cooling system. And there was a lot of hardness in it. a lot of calcium, all the stuff. We tried to treat it. You would still get a lot of hardness. And so these condenser tubes would build up with like calcium carbonate and other things in it. Okay, now this is the fun fact for you guys to remember, right? So the way we would clean those, because every once in a while we'd have to take the condenser down and clean it because you get too high pressure, you couldn't get the water through. We'd literally buy boxes of tampons. We'd stick a tampon in each of the tubes and we'd air blast them through to clean out our condensers. And so about once a year, think about, we had Sam's Club, we have Costco here, same idea. We'd order boxes, tampons, clean out our condensers. Fun fact you guys can share with your friends about cleaning condensers for power plants. All right. So that condenser is the way of cross-exchanging, right, your cooling water with your steam. The way you get cool water to cross-exchange can be done in a couple different ways. One of it is like we were doing, we used evaporative cooling. And so that evaporative cooling, basically you have, and we have some of these on campus. If you guys go to the Central Energy Facility, there's some behind it. You're putting water at the top, the condensing water at the top, and it falls down. And as it's falling down, it evaporates. So you lose a lot of water, but evaporation cools the water. And so the water that's at the bottom of the evaporative cooling system is cool. And then you can use that to cool your steam. And then you put it back into your evaporator and you do the process again. So it's a very lossy way in terms of water loss, of cooling the water for your condensing water, but it is the primary way today that we're cooling our thermal power plants. And the reason it's the primary way that we're doing this today is because in many places, like in California, for example, we're no longer want to use once-through cooling. It's no longer legal to use once-through cooling in California. Once-through cooling is where you're taking it out of the ocean or a river, you're running it through your condenser, you're putting it back into the ocean or river, but it's 20 degrees warmer than it was. And that has impacts on the lake, the river, the ocean that you're taking it out of. And so that's why California no longer allows it, is because the environmental impacts of the once-through cooling. It's a different challenge when you're talking about using, we use river water as our makeup, but even potable water for your condensing systems, you're just losing a lot of water for doing this cooling. So it's just like a different challenge. Dry cooling, I put this kind of up here for completeness. We don't do a lot of this because it's very inefficient. We only do this where there isn't water. So some of our solar thermal power plants, Ivanpah is a big one down in Southern California and Nevada, they don't have water to use as cooling, and so they have to use air. You can imagine the air in the desert is not the best cooling medium, so it's pretty inefficient because it's hot air, but they're trying to cool the air in order to use that as cooling. So you tend to see pretty low efficiency in these kind of systems because you don't have a very cold, right? Might have a really hot, but not a very cold. Okay, so talking a little bit more about the once-through cooling, we used to go see this down in Moss Landing. So Moss Landing is kind of between here and Monterey. It's like along the way. If you ever drive down to Monterey, you'll see it because you'll see the old stacks that were from when it was an oil-fired power plant. It used to be an oil-fired power plant. Then it was a combined cycle natural gas power plant. Now it's primarily battery storage. They have a couple battery storage systems. If you look it up in the news, they just had a big fire there in January that Adrian was talking about on Wednesday. So they've been in the news for that. But it's kind of gone through this progression where we're continuing to utilize the electricity transmission and distribution system there, but it's kind of changed on in what purpose. So the natural gas power plant and the oil-fired power plant were once pulled through cooling there. It's a very, it's right on Monterey Bay. They were using the ocean water and bringing in the ocean water. They'd bring it in on these big screens. These screens were rotating. You can see that things like jellyfish, other stuff would get stuck on the screens. The screens would put it on a conveyor belt and it would go into a dumpster. And so we would go see this. There's like crabs everywhere, all these different things that just kind of got stuck on these screens as they're bringing in the ocean water. And so this was a lot of the reason why California no longer allows once-through cooling. We still do it in some places because there is kind of like a time frame where power plants have to get off. They're given like 5 years or 8 years or whatever to get off of the once-through cooling. So when we start talking about nuclear, the one remaining nuclear power plant in California still does once-through cooling ocean water down in San Luis Obispo. So that's one of the big sites. It still uses once-through cooling. So you can kind of get a sense of the impact of these kind of systems. The other way to do it is evaporative cooling. So this is actually an old picture of Rancho Seco, which is another, it's a decommissioned nuclear power plant that we go see. Now it's pretty much a solar farm. So these things are still there, but the land around it has all been turned into solar. Again, reutilizing that existing transmission and distribution system. But this is what large-scale evaporative cooling looks like, right? So in these, they have water that's being sprayed at the top. The air comes through on the bottom, so the air is kind of rushing up through, causing that evaporation as it comes down. And so the water that you collect at the bottom is cold because evaporation is cooling. So you guys should all know the answer to this question that I have next. Would a steam cycle power plant be more efficient in the summer or the winter? Winter. Yeah. So your hot doesn't change that much. Your boiler isn't really affected by the seasons in terms of like you're burning the coal or whatever. It's going to be whatever temperature it is. But the winter is when it is going to be more efficient because of your condensing water. Your condensing system, whether it's evaporative or once through, is going to be colder. And so you have a colder sink in the winter. So when you look at the data for capacity of our power plants, a lot of times, like the EIA will report it in net summer capacity because that's like the worst case. That's like the lowest their capacity is going to be in the summer. And so you actually see them reported as net summer capacity because they have less capacity in the summer than they do in the winter. So I talked about how like steam, expands metals. So when you go to some of our systems, this happens to be a picture from the geysers, but you can see it even at Central Energy Facility, things like that. These are steam lines. They're insulated, so there's pipes inside those, and those are insulation that goes around it. And you see these jogs in the lines. That's to allow for expansion and contraction. And oftentimes, you can see they're on these little stanchions. Oftentimes, they're not connected to it. It's more like a platform that allows it to move back and forth a little bit. And the reason is if you had something that was just straight and it's expanded, you'd be breaking it at either end, right? Every time you were expanding that pipe. But if you put a bend in it, now you can have some give, and it can still, at the ends, be rigid. And so you'll see that in our steam cycle systems. We see it a lot at the geysers because there we're moving geothermal steam from one location all the way to the power plant. So you're moving the steam over, relatively long distances. We tend to try not to move steam around because you have lots of losses, even with lots of insulation. So you want to do your generation right close to where you're producing your steam. Okay, so let's talk about some other thermal power plants. So we typically use steam. Steam is kind of the most efficient way of doing our thermal power plants, but in some cases we don't have a high enough temperature source to make steam. And so when that happens, we use some other fluid, some working fluid, isopentane, isobutane, something that evaporates at a lower temperature than water. So it's less efficient, but if we only have something that's like relatively low temperature, we got to use a different working fluid. The two cases where we use that, ocean thermal, which we'll talk more about in the ocean lecture, where we're using just the warm temperature of the surface water as our heat source, pretty low temperature. We don't do that a lot. Geothermal is the other place, and this is where there's a lot of growth going on. We use something called the binary cycle for geothermal, where we can use we can just use warm water from a geothermal reservoir with that working fluid and still do basically a thermal power plant, just using a working fluid instead of the steam. Okay, so same idea. You still have to have a hot source. You still have to have a cold sink. All those other elements, you're just using a different working fluid. Okay, let's switch gears. So that was our steam cycle or our type of thermal power plants. Let's talk about gas turbines. So I mentioned gas turbines is basically just like an airplane engine on the ground. So just picture airplane engine. Again, we're using it to create rotational mechanical energy to turn our turbine. Really fast on and off. This is what for a long time we really used to fill the peaks and valleys in our electricity generation in order to meet real-time demand. We're using batteries more and more for this now that they're cost competitive, but we still have a lot of natural gas turbines that are peaking. Now, this is, like I said, relatively inefficient. And part of the reason is basically you're just using the air as your cold sink. This is still a heat engine, but you don't have a condensing system. You don't have that cooling water to make it a really cold sink. And so in this case, it's really just air as your cold sink. It's not going to be as efficient. These are cheaper to build, operate really quickly, but you don't want to operate them a lot because the more you operate them, the more expensive it's going to be. This is just what one looks like. You guys saw a video, hopefully, on Canvas. It's just kind of like a airplane engine strapped to the ground. Yeah.
Why do gas turbines get more expensive the more they are used?
Yeah, if you're thinking about cost per electricity that you're getting out compared to other resources, and I have a chart on this that might make that clearer. Because it's low efficiency, basically it's cheap to build, so you have low capital costs, but it's expensive to run. And so what you want for these assets is to run them a low number of hours in the year. And then the assets that you want to be running a lot of hours in the year, oftentimes like a nuclear power plant might be more expensive up front, but once you've invested that capital, you really want to run it and do most electricity production there because it is lower cost per electricity production. Does that make sense? Yeah, so we tend to want to run these as little as possible. They're really just frequency regulation and meeting that peak demand because they're really fast response. That's a great question. Okay, and then the natural gas growth that we've seen in the United States has primarily been in something called combined cycle. So in combined cycle, we're combining those two systems. We have our gas turbine that still comes online really quickly. You can start to meet peak demand with that gas turbine. And as you bring that online, you're also using the exhaust to slowly heat up and start producing steam. And so you're already producing electricity with that gas turbine. You're starting to warm up your steam cycle, and then you can also run a steam cycle that's going to give you additional electricity generation from the same gas that's going into your gas turbine. So it is like producing more electricity from the same amount of fuel. So you can imagine the efficiency of this is a lot better because you have both systems. The response rates are a lot better because you have both systems. This is a lot what we're doing with our natural gas systems, is doing this. This is something that makes the natural gas thermal power plants a lot more desirable on the grid than like a coal-fired or a nuclear power plant. They don't have that intermediate quick response and the steam cycle. And so, you know, we talked about in the coal lecture the efforts right now to really revitalize the coal industry in the United States. This makes it hard because operators really like this flexibility that natural gas gives them, even if you're not considering all of the other things like having to deal with solid waste and all the other things with coal, right? This is a flexible system, tends to be pretty efficient, that they can use on the grid. And right now we have lots of natural gas domestically. You can even take this a step further and do something called cogeneration, which we've talked a little bit about. We had a cogeneration plant on campus before we took it off and built the central energy facility. Cogeneration is basically using the low temperature heat and using it for something. So for our steam cycle, we really need high temperature heat, but after that process, you can get some low temperature heat that could be used for space heating or low temperature uses, agriculture, you can use it in greenhouses, things like that. That obviously would increase the efficiency overall. We see cogeneration more like district heating, things kind of like that on either industrial or university campuses or in Europe. Europe has a lot more district heating, cogeneration type things. The challenge again there is, especially here in the United States, is our power plants tend to be far away from where those low temperature needs are, and it's hard to move heat around. Heat is very lossy to move around, even in very highly insulated things. So cogeneration really kind of has to be very close to where you're creating that heat source. Okay, and just give you a sense of the different efficiencies now that we've gone through this. And we're going to talk about heat rate and then the efficiency of the different ones. So efficiency is kind of intuitive, right? It's basically output over input, like how much useful output am I getting over the amount of energy I had to put in. That's your efficiency. Well, in the industry, in the electricity industry, when they're thinking about efficiency, they instead talk about something called heat rate. Heat rate is something when they're thinking about the thermal power plants. And so heat rate is looking at the energy of the fuel I put in and the amount of electricity I get out. It is often in these mixed units. Those are both energy units. It's usually BTU per kilowatt hours. And that's just because we measure coal in BTUs and we measure electricity in kilowatt hours. And who wants to do unit conversions when you're in industry? And so they just talk about heat rate and leave it in the units that we often measure those quantities in. You can make a heat rate into an efficiency. It's just the inverse and making it unitless, right? Because those are both energy units. You can convert from BTUs to kilowatts and make it an efficiency. But just to be familiar with lingo, heat rate is what industry is talking about. And so you can think about heat rate as a measure of efficiency for a thermal power plant. What do those efficiencies look like now that we've talked about it? I told you gas turbines, less efficient, and then our steam cycle, our combined cycles, some of our combined cycles are getting up more into 60% efficient, so we're getting better and better. These are still averages, so some of those are some of our older systems. And then cogeneration is even better in terms of efficiency, making more use of that energy, that heat from your fuel. Okay, a few more key terms that I think is important to talk about when we're talking about the use of our assets, our electricity generating assets. And so two terms that sometimes people get confused are capacity and capacity factor. Capacity is literally the power generating capability of that power plant. It's a 50 megawatt, that'd be really little. It's a 1 gigawatt nuclear power plant. That's pretty typical, okay? That's the capacity. Capacity factor is a measure of the utilization of that asset. And that utilization can be influenced by lots of things. For solar, it's influenced by whether the sun is out. For a nuclear power plant, it might be influenced by how often you have to shut it down in order to change out the fuel, right? So reliability, maintenance, all these things come into capacity factor. Capacity factor is really just like if it could run 100% full-time over the time period at its capacity divided by how much it actually runs. That's its capacity factor. And so it's pretty easy to think about. It's the energy produced over the maximum producible. This is just an example, and I won't make you do this, but you can refer back to it. You can do it for a whole industry. So if we were looking at all the coal plants in 2014, their full capacity was 300 gigawatts. This is how much they actually produced. Is this under the blue line? You divide those by each other, the generation divided by the max generation. So their capacity factor was about 60%. Again, influenced by fuel availability, by demand, by maintenance, by anything and everything. Doesn't matter why they weren't operating. This is how much they operated. That's capacity factor. Industry often talks about net capacity factor. That's just also taking into account, like a coal-fired power plant has a little bit of electricity draw for its own needs, and you kind of take that out. Whether that's 3%, 10%, depends on the facility. Some of them have a lot more electricity use on site. So if we're looking at average capacity factors for our different types of resources across our electricity system, this is what it looks like for the United States. You can see our base loads, nuclear, geothermal, tend to be very high. Coal is also a base load, has less capacity factor. It's partly because demand for those resources have gone down. But You can see nuclear, very, very high capacity factor. That's not only because we run our nuclear power plants very well, we have very little downtime on our nuclear power plants, but it's also because once you have them up and running, you can't vary the load. It can't load follow. And so something like our natural gas combined cycle power plants are doing much more up, down, up, down, up, down, trying to incorporate renewables, trying to incorporate changes in demand. Nuclear is just up and running. So it has a very, very high capacity factor. Geothermal, most of this is maintenance. It's just up and running as much as we can. It's very low cost once you've invested. You can see things like solar. It's going to have a low capacity factor because the sun's only on half of the day anyway, right? So it's not going to be at full capacity 24 hours a day ever. So it's going to have a relatively low capacity factor. Our peaking natural gas turbines, you can see we don't want to run them unless we have to. We talked about this is expensive. So those are just the single cycle gas turbines. We're only using them to fill when we have to. We talked a little bit about this already this week, so this is kind of just a summary slide of some of the terminology we've talked about. But for our electricity generation resources, some of the things that are really valuable right now, really valued on the grid, is that ramp rate. How fast can you come online? And a lot of that, we talked about the duck curve. It's because we have kind of that solar wind profile. We really want things that are able to help with incorporating that. And so ramp rate, flexible generation is really valuable. The profile for load demands in terms of not just daily, but yearly vary depending on where you are in the world. So I just want to give you a sense. We talk a lot here in the United States. We talk about air conditioning load in the summer. That's where we see a lot of our peak. That's not necessarily a peak electricity in other countries. You can see there's a lot less variation in places like Australia, where you have less peaky demand over the year. Places like France, they see more peak in the winter when they're using electricity for heating services rather than like a summer service. But all of these things are changing with climate change. We've talked about air conditioning load, for example, is something that is growing worldwide as people are trying to manage the excess heat they're seeing. So this is a chart that I mentioned earlier about looking at the cost curves for a peak simple cycle gas turbine that's really cheap to build, but it gets expensive to operate. And then our natural gas combined cycle, which is a little more expensive to build, but much cheaper to operate. And so this is why you want these online for reliability purposes, but you don't want to run them any more than you have to. You want to run your more efficient, bigger power plant. Now you guys are going to do some math, Friday math, to figure out how to calculate levelized cost of energy. All right, let's talk about levelized cost of energy. Levelized cost of energy is a tool for us to be able to compare the cost of different resources, given that they're so very different in terms of when you pay those costs and the lifetime of the project. And so I have this little visual here. You've got some wind turbines, you've got a full coal-fired power plant. Those have very different cost profiles over the life of the project. So when we're levelizing the cost, we're giving it an annual cost that is the same over the lifetime of the project, so we're able to compare it amongst these very different resources. Wind and solar tend to be very capital intensive up front, but they have free fuel costs and relatively low maintenance costs, so their costs over time are low. Whereas something like a coal-fired power plant, you have some of that upfront capital costs, but you also have fuel costs over the life of the project. And so those have to be taken into account. So all of that is taken into account by this process of levelizing the cost. So this is the chart. You're going to see lots of this chart. You've already seen it. Levelized cost of energy. Lazard puts this out every year. They base this on actual projects. So you can see why there's a huge range of these costs, because they're actually looking at real projects that are being implemented in most of these cases. And so there's kind of a variation on for different reasons. But these are our combined cycle, coal, nuclear, our gas peaking plants down here on the bottom, and then our renewables at the top, and at different levels. So you can see residential, commercial, utility. You're going to see different costs for those different kind of projects. It is levelized in terms of the money, so we're making it the same annually over the lifetime of the project, and it's levelized in terms of the electricity production. And so now we can compare it because this is dollars per electricity produced. And so you can really compare these resources on their cost basis. The first thing you got to do is start thinking about discounting and present value. Don't worry, we're not going to get too deep into this, but discounting and present value. Really the concept to think about is that cash today is more valuable than cash in the future. So we discount the value of cash in the future when we're thinking about present value. For levelized costs, we're really thinking about net present value because it's a stream of cash over the future that we're bringing to today's value. So just to give a really easy example, what is the present value of 3 payments that I have to make at 5% interest? I have to pay $100 today, $120 in 1 year, $200 in 2 years. How much would I have to put in the bank today if I'm getting 5% interest to make those payments? Okay, and so our net present value, 100, and then you have to think about a year from now at 5% interest for that payment, 2 years from now, so it's squared at that 5% interest. I have to put $395 in the bank today at 5% interest to make those payments. When we are talking about net present value and the annualization of the capital costs of these projects, we use something called the capital recovery factor. So it's this equation basically. Your annual payment for your project is the principal that you put in times this capital recovery factor. We won't make you memorize this ever, but you will use this in calculating your annual payment for the capital investment that you're making on your project. This is the amortization. This is levelizing it over the lifetime of your loan, your capital loan. So if I have $10,000 in student loans at 6% interest for a 10-year period, you can use this capital recovery factor and the principal to figure out what your annual payments are. This is annualizing the cost of your capital. Okay, so that's annualizing your cost. A lot of that is your capital. You then need to add your additional annual costs to it. And so that's maintenance, operating, any fuel cost, all of that has to be added. And in order to get a levelized cost overall. When we're doing this, so basically your levelized cost of energy would be that annualized cost that we just figured out, divided by annual generation, and you'll just assume the generation is the same every year. Annualizing generation is just kind of an estimate, an average of what you expected the generation to be over the lifetime of the project by year. So you have your capital cost times your capital recovery factor. You have annual operating costs, so that's your maintenance, your fuel, whatever it is, divided by your annual generation to give you your levelized cost. So we're going to do an example, and then you'll get to do some of this in your homework. This is a very simple example. So I have a 10 megawatt power plant. It's tiny. That costs $1 million, but lasts only 2 years. So that's a terrible investment. You would never do that. Capacity factor is 90%. Capacity factor is important because that's telling you're often given the capacity of your plant. But in order to figure out your generation, you need to know what your capacity factor is going to be. How much is it actually going to produce? What's going to operate? So capacity factor can help you calculate your analyzed generation, right? My interest is 5%. Awesome, that'd be relatively low right now. I have my fuel and operating costs. Sometimes your operating costs are given per megawatt hour or per kilowatt hour because a lot of times operations, fuel costs, those depend on how much electricity you're producing, right? And your fuel is going to depend on how much electricity you're producing. So you would need to know how much you're producing before you can figure out what your annual operating costs are, right? So a lot of times it's given like that. And then you want to figure out what your LCOE is. So here's your calculations. Annual generation, I have my capacity factor times the capacity of my plant times the number of hours in the year. This is how much electricity I'm producing every year in my little power plant. My operating costs. So I have to figure out, I have to use the amount of electricity I'm producing every year times my operating costs. So that gives me like my fuel costs. So that's how much money I'm spending on operating. And then I have to figure out my capital costs. Remember, it's for 2 years. It's $1 million. This is my capital recovery factor. That's my annualized capital cost. And so you can put that all together. You can add your costs together. You divide it by your production. You get $1 per megawatt hour. In the last 10 minutes, I just want to talk a little bit about the environmental impacts of our electricity generation. We're going to get more into the details of these when we get to each resource, but just for some framing and talk about kind of the future of what's happening in our electricity system. So there's a lot of environmental issues related just to the electricity generation piece of our electricity system, and that's what we're going to be talking about today. But this is just listing some of them. Some of them pretty obvious depending on your resource: greenhouse gases, air pollution, water use, thermal pollution, solid waste, land use. It's an industrial facility a lot of times, depending on what it is. With the nuclear, we have to worry about power plant decommissioning, things like that. So a lot of environmental aspects that we have to think about and regulate on our power plants. In terms of greenhouse gas emissions, electricity production is about a third of the greenhouse gas emissions globally. It's about a quarter of the greenhouse gas emissions domestically in terms of our energy greenhouse gas. So you can see a significant source of greenhouse gases. An interesting study that was done just a few years ago kind of looked at the electricity system globally and where are the worst polluters, where are the most carbon emissions coming from in terms of greenhouse gas emissions. You can see a lot of them are in Asia, although one of them's in Poland. That's a coal-fired power plant there. The study basically found if we could shut down 5% of the worst, we could cut carbon emissions by 75% from the electricity system. That just gives you a sense that some of these are very large coal-fired power plants. It's really our coal-fired power plants that are the source of most of the greenhouse gas emissions from our power system. And this is just breaking it down by country on how impactful, just looking at even the largest coal-fired power plants, if we could replace them with something else, it could be really impactful. And of course, in some ways this chart's kind of silly, but the CO2 emissions for selected sources, coal is going to be the largest, followed by natural gas, and then these guys are zero carbon emission resources on our electricity system. U.S. policy. We had a policy put in place by the Biden administration that basically said that new generating resources had to be just as good as a natural gas power plant in terms of greenhouse gas emissions. That basically said you couldn't build coal-fired power plants because they produced more greenhouse gas emissions than our best natural gas plants. This hasn't been rolled back yet, but it's likely to be rolled back in terms of some of these policies of trying to lower greenhouse gas emissions domestically. Air pollution has gotten a lot better from our electricity system, even as we've continued to operate some of these coal-fired power plants. As you saw, hopefully in the video, there are ways to scrub out a lot of those air pollutants like sulfur. So you may not know, but especially in the 80s and 90s, acid rain was a major challenge in the Midwest and the eastern part of the United States. And that acid rain was really from sulfur emissions from coal-fired power plants, primarily in the Midwest, that was falling on the East Coast. And so you can see the measurements of acid rain in that upper picture. What does acid rain do? I mean, obviously it's not good for us, but it melts things like statues. This is a picture from Germany just because they have a really good picture of it, but same idea. Our statues were melting. Buildings were melting, things like that from the acid rain. And of course, it impacts our ecosystems, our lakes, our waters, everything else. It was a challenge that had to be addressed federally because it's a cross-state pollution. So once things start to cross states, you have to have a federal policy. It's not like, Connecticut could complain to Ohio and say, you guys have to lower your emissions because you're impacting us. You really have to have something that's cross-state to look at that. So we have policies. At the time, actually George Bush put into place an acid rain cap and trade system that capped the amount of sulfur emissions that were allowed each year. You could trade credits, but it continued to lower and lower sulfur emissions. It was a really successful program where we really don't see acid rain as a problem today from those programs. So we've done a lot in reducing our sulfur emissions and our NOx emissions. Of course, that's going to continue to decline now that we're taking a lot of coal offline. Haven't made a lot of progress on greenhouse gas emissions except for just the coal-fired power plants coming offline. Water is a big use in our system. So I'm showing you two charts here. This is consumption in the electricity generation. This is kind of thinking about cooling and things like that. And so you can see some of them are much more water intensive than others, and thinking about the use of our fresh water. We'll talk about this more as we get into each resource and how water intensive some of our resources can be. Water use in the electric power sector is on the decline, and a lot of that is just really just the shutdown of both nuclear and coal-fired power plants. So it says water efficiency gains, but it's shutting down old plants. That's really a lot of that. Okay, and where are we going? Well, there's a few things to think about, and we've talked about them already. Our electricity demand is expected to go up in the United States. It's been flat for a long time. We're growing electricity access globally, so we're expecting that to continue to grow. And electricity share of final energy consumption has been relatively flat, but that's also expected to grow. And that's just an indication of how much we're electrifying space heating and cooling, how much we're electrifying cooking, how much we're electrifying transportation, all of those end-use sectors. Share of renewable electricity generation is expected to continue to grow. Much of the growth and demand we're expecting to see in the developing world. But more recently, we're also expecting to see more growth in the developed world, as we've talked about with AI and things like that. In the United States, our mix continues to change. So this is just giving you a summary of where the growth has been and where we've been shutting down coal-fired and nuclear power plants, which we'll talk about more. As I said, if you looked at our demand, which is that curve, the red line, it's been relatively flat, even some downturn in terms of electricity demand. And so we've been really using renewables and things that we're adding onto the grid to replace generation rather than growing generation. And so that's really going to be the change in mix. And so we talk about future generation is, okay, we've been in this flat space. What happens if we are going into a space where we're seeing rising electricity demand? Will we continue to decarbonize at the rate we have been if we're also increasing demand for electricity? And so that is a question of what's going to happen. How fast will that fuel switching be on our electricity grid? So these are some predictions for solar, wind, where nuclear will be. Because we're growing electricity demands, not just in places we've talked about, but even in homes, space heating, water heating, cooking, growth in air conditioning, things like that. So as that demand grows, we're going to have to see how the generation of our electricity plays out. All right, awesome. Thanks so much, guys, for being here with me on a Friday.